This video starts a series of videos dedicated to hydraulic fracturing. Before getting into the analysis of fracture propagation, we're going to first see how these fractures can start. And in order to do that, let's think about a half wellbore model. At least that's what I have drawn in here. But try to think about the entire wellbore with the full domain. In this model, if we have in situ stresses, a pressure inside the wellbore, we could find instances of shear and tensile failure around the wellbore depending on the orientation of the wellbore and depending on the orientation of the stresses with respect to the wellbore. Let's assume that we are in conditions of normal faulting, and let's also use the elastic solution from Kirsch for isotropic rock. The Kirsch solution tells us and allows us to calculate the hoop stress and the radial stress around the wellbore. And for this solution at the wall of the wellbore, we see that depending on the angle theta, measured from, in this case, SH max along the wellbore, we're going to have a value of the hoop stress that is going to vary with the cosine of the angle 2 theta. In regions in which theta is equal to 0 or pi, I'm going to have the lowest hoop stress possible. And if I match that to the tensile strength, that's what is going to give me what is called the breakdown pressure, solving for the pressure in the wellbore that gets to that value of tensile strength. In terms of the Mohr circle, that means that if I have an initial Mohr circle somewhere over here, by the actions of the pressure in the wellbore and by making just the wellbore, stresses are going to change at the wall of the wellbore. And at theta equal to 0 or pi, I might get to a condition in which I have tensile failure. So the Mohr circle, the lowest value of principal stress, gets to the tensile strength limit. For the sake of completeness, let's see what would happen if theta were to be equal to pi over 2 or 3 pi over 2. In that case, you will get to this location, and that's with pi over 2. And that's where you will have a shear failure and a wellbore breakout. So basically, the Mohr circle goes from the initial condition to another condition, like, for example, this one, with a Mohr circle that goes into shear failure. All right, but in this case, let's keep the discussion just for the tensile failure, because we want to investigate what is the pressure in the wellbore needed to get the rock into tensile failure at the wellbore. And as we said, that's what is called the breakdown pressure. And just by substituting theta here for 0 or pi, then we obtain this equation that we have over here. And when we get to the breakdown pressure, then, and we go a little bit beyond, we are going to fracture the rock in tension, and we obtain a tensile failure that is going to be formed by a plane which is perpendicular to the hoop stress at this location. And in this case, that's going to be the plane, these two planes. Remember that I'm not drawing the other half of the wellbore, so these are going to be planes in the middle. All right, that breakdown pressure, PB, depends on pore pressure, depends on stress anisotropy, and also depends on tensile strength. It's more or less obvious that in order to fracture the wellbore, you might need a pressure which is at least higher than the pore pressure. What is less obvious is the effect of stress anisotropy. But as we're going to see, the higher the stress anisotropy, the lower the breakdown pressure is going to be. And also makes sense that the tensile strength is going to be an important factor here, because the higher the tensile strength, the higher is going to be the pressure needed to start a hydraulic fracture at this location. Or in this case, let's just keep it and say is going to be a tensile fracture. All right, let's see what we do with this solution of the breakdown pressure now. In order to do that, we're going to see two cases. The first case, case number 1, is going to be the case that we're going to call an isotropic case. Or we could be a little bit more specific in this case, and since we're talking about the horizontal wellbore, we could call this horizontal stress anisotropy. This happens, for example, when you have a small tectonic strains, so that sigma h max is equal to sigma h min. And just to make it simpler, let's just call it sigma h. If you replace sigma h here, then you'll have negative 1 sigma h plus 3 sigma h. That's going to be 2 sigma h. And so the breakdown pressure is going to reduce to this simpler equation, where you can see that in an isotropic environment, in order to get a tensile fracture, you also need to overcome a term that is a result of the stress anisotropy. If we go to the other extreme and we consider a large stress anisotropy, horizontal anisotropy, let me add here horizontal. In this case, we are going to have a horizontal anisotropy which is quite large, and the breakdown pressure is going to be affected by that. In this case, let's assume that more or less a maximum stress anisotropy in which sigma h max effective is equal to 3 times sigma h min effective. And this comes from here, from the reasoning of the equilibrium of faults, and assuming that the maximum effective principal stress is a function of the minimum effective principal stress to the friction parameter Q, which implies that this place is under the limit of the maximum horizontal stress or the minimum horizontal stress, which is caused or which is the result of the equilibrium in faults. In this example, which it's a little bit easier to show, is an example for normal faulting, in which sigma h min is the lowest possible value as a result or as a function of sigma v. In this case over here, I'm assuming the maximum horizontal stress anisotropy, which is a result of a strike slip, in which sigma h max is going to be q times sigma h min, where q, we can assume that that's more or less equal to 3. So that's why we have these 3 over here. And when that happens, then we see that if sigma h max is equal to 3 sigma h min, then this equation, these two terms are going to cancel out. And what this is telling me is that in case number 2 of a large stress anisotropy, almost the maximum, the breakdown pressure is going to depend on the pore pressure too, but it's not going to be a function of the effective horizontal stress. It's just a function of the tensile strength. So what this equation really means is that when you have a large stress anisotropy, that's going to favor lowering the breakdown pressure or the fracture gradient. It's going to be easier to fracture a wellbore in that condition. Why? Because the stress anisotropy is creating a variation of the hoop stress around the wellbore that is favoring these low values of hoop stress so that they get closer to the tensile value of tensile strength. When you have an isotropy, this amplitude is a lot smaller, even 0. Okay, so let's see now how we can extend this concept of breakdown pressure to a field hydraulic fracturing test. There are two types of tests that are common that include fracturing. One is the Lickhoff test done for drilling, and the other one is the diagnostic fracture initiation test, also known as the DFID test, and which is used for completions and hydraulic fracturing. Similarly, also you have the mini frac test that is a similar version of what we're going to see now. To keep a little bit the problem easier, let's analyze and make a schematic here for the leak-off test. In the leak-off test, what is done is to pressurize an uncased, most often an uncased section of the wellbore. After you set your casing, you isolate that section with a pucker, then you start injecting a fluid at a constant injection rate, and because the fluid cannot go anywhere other than the pore space of the rock, then the pressure is going to start to increase. And how fast it increases is going to depend on several factors. Like, for example, for the leak-off test, on the filter cake that forms around the wellbore, on the permeability of the formation, and many other things. But it is going to go up. So if we conduct a constant injection rate test like this one, sometimes we stop. When we don't inject anything, the pressure is going to be just the original pressure. Let's say here a little bit higher than the pore pressure of this formation. But as soon as we start injecting, the pressure is going to increase. The question here is, how far is this pressure going to increase in the wellbore? And that's when we're going to use our equation of the breakdown pressure. We calculated before, and this is the example for case number 1, that this breakdown pressure would be a function of the pore pressure plus 2 sigma h, and you see this 2 sigma h in here, plus the tensile strength. So this will be the predicted value of the breakdown pressure for this particular wellbore. And what that means is that if I continue here increasing the pressure, at some point the bottom hole pressure is going to go into a tensile failure. So when that happens, this wellbore, and here I'm just drawing a cross-section of the wellbore, is going to go from being an intact rock, and we're assuming here an intact rock, to have a tensile fracture at the wall of the wellbore. That's when I reach the value of PV calculated with the equation above. What happens if we continue injecting and increasing the pressure in the wellbore? Well, it's often seen that this pressure is going to go a little bit higher, and then it's going to go eventually through a peak. And that peak is going to depend on several factors, like, for example, how fast this fracture is propagating, the viscosity of the fluids, and many other things. But let's try to think the problem on the stage in which the fracture is already propagating. So at some point, this well is going to create a fracture which is long enough that it's not a small tensile fracture anymore, but now it's a large fracture that has fluid that is going through the fracture, and the leak off now is not only happening through the wellbore. Remember that we have assumed an uncased completion here, or an uncased wellbore, and the leak off is also going to be from the walls of the rock, the newly created fractures. And also we're going to have flow that goes from the well into the fracture. This is the regime in which we will have a full propagation. And as you may imagine, that propagation pressure is going to depend on several factors, but principally is going to depend on what is the least principal stress. In this case, sigma or SH mean, actually the total stress. We're assuming that we have a good enough filter cake, so the fracture, in order to open, has to overcome the least principal stress, total SH mean. What that means is that notice that here pore pressure plus sigma h, that's going to be SH or SH mean. And that fracture, in order to propagate, is going to have to be a little bit higher than that value of SH mean, or the least principal stress. And the difference between that minimum principal stress and the fracture propagation pressure is going to be what is called the net pressure, and is the pressure in the fracture minus the least principal stress. And the pressure at which the fracture propagates is called the fracture propagation pressure. We're not in conditions yet to tell what this fracture propagation pressure is, but we're going to see that later on. All right, so as we have this peak and we have this fracture propagation pressure, then eventually these two have to connect. And this is what is going to happen. When you initiate a fracture in a wellbore, first there is going to be a stage of pressurization. You go to the breakdown pressure over a peak, then this rolls over into more or less, it will depend, this is flat or increases or decreases with time. We're going to see that later on, but let's assume now it goes into a more or less a constant value of propagation pressure. Then that's going to be what we said is going to be the fracture propagation pressure. And at that stage, I have fluid going into the fracture and also leaking off from the wellbore and from the fracture tube. All right, eventually we're going to stop injecting at some time, and at that point the pressure signature is going to, as soon as we stop the pumps, because the fluid is not flowing anymore into the fracture, and I don't need that viscous energy in order for the fluid flow to go into the fracture, there is going to be a decay of the pressure, and that is what is called instantaneous shut-in pressure. Instantaneous shut-in pressure, also known, actually this is, we can summarize it, we can put the acronyms as FPP, fracture propagation pressure. This is ISIP, instantaneous shut-in pressure. And as soon as we shut in the well, then in the period of the instantaneous shut-in pressure, what is going to happen in the wellbore is that the fracture is going to be still open. There is still going to be leak off from the wellbore and from the fractures into the formation, but I'm not going to have any more fluid going through the fracture because there is no pressure, no energy that is pushing that. Eventually, the fluid which is in the fractures and in the wellbore I'm gonna try to leak off into the formation, and the fracture is going to close. The value at which that happens, and as the pressure decreases, is what is known as the fracture closure pressure. So after I shut in the pumps and after that instantaneous decrease in the pressure is going to decay slowly and eventually go into equilibrium with whatever the pore pressure is in the formation. That's the point in which there is not going to be any more gradient of pressure. And the value at which the fracture closes, this wall gets to touch this wall again, is what is known as the fracture closure pressure, or also FCP. And at the fracture closure pressure, at that time, what we will see is that this fracture has already closed, so the walls of the fracture of the rock get to contact with each other. Let's assume that the permeability of the fracture is very small. In that case, the leak off will just continue from the wellbore, and not from the fracture anymore, because the gradient of pressure between here and here is the same as you will have between, for example, here and there. So this is going to resemble more like a radial flow, and the decay is going to be slower than before, and the pressure at which the fracture closes, that's going to be called the fracture closure pressure. Okay, so now we see the full signature of the expected response of the initiation and propagation of a hydraulic fracture done with the Likov test, and a similar behavior is going to happen when you do this with a fracturing fluid from a perforation or from a small section in the wellbore. It's very similar. The mechanics is the same. All right. The maximum value, then we predict that with the breakdown pressure. The fracture propagation pressure, that's something that we need a few more things and a few more physical models in order to predict that. So that's what we're going to do next in following lectures. All right, here we solve and obtain this signature for case number 1. What will happen for case number 2, in which I have a high stress anisotropy? In case number 2, I would see a different signature of the pressure as a function of time. Why? Because the breakdown pressure now is different. Notice that breakdown pressure is going to be just a function of pore pressure and the tensile strength. So if you have a given tensile strength and you also have a least effective, a horizontal effective stress, the fracture, in order to propagate, is going to have to be higher than the least principal stress, S3. I'm going to need also an additional pressure in order for that fracture to propagate. We call that the net pressure. But eventually I could go without a defined peak as I had before, because now the stress anisotropy is making it easier for this fracture to form. And eventually I could even have the rock fracturing in tension at the wellbore before I get to the fracture propagation pressure. And that's because of the effect of the stress anisotropy. All right, let's see now how we apply this concept of the initiation of a tensile fracture at the well into 3 dimensions and with wellbores at different orientations. All right, now we're going to go into a 3D model or into a 3D block in which I have 3 wells, 1, 2, and 3, and these wells, 1 is vertical, 2 and 3 are horizontal, and they are drilled at different orientations. We are also assuming here that we are under normal faulting stress regime, and that, of course, the maximum principal stress is SV. All right, in this case, what we are going to observe is the following. Let's go first with case number 1. Case number 1, extending the discussion that we had before, is what we see over here. And in that case, if I want to analyze where the tensile fracture would start, that would be in the location that coincides with the direction of SH max. This is exactly what we have seen before. This is the point at which in the Kirch's equation theta is equal to 0. And that plane, we can see, is going to be already perpendicular to the least principal stress. So if this fracture were to grow and extend away from the wellbore and grow into a larger hydraulic fracture, this one will grow something like this, extending in the direction perpendicular to SH mean, and the same in the other direction, of course. And this is exactly what you see in case number 1, that if I were to start a hydraulic fracture from an uncased open hole wellbore, in this case, the fracture would tend to grow perpendicular to SH mean. That's what we would expect for the ideal orientation of a planar fracture. What happens in number 2? In number 2, if I were to have also an uncased wellbore and I pressurize it so that the rock starts to fail in tensile failure, I will have this case. And in that case, my tensile fractures would align with SV. Why? Because SV is larger than SH mean, and that's the point at which, in the Kirsch equation, theta is equal to 0. You can see that those planes and that hoop stress coincides with the least principal stress, also SH mean. So this is a plane which is already perpendicular to SH mean. In that case, if I were to continue increasing the pressure, the fracture would continue growing in the same plane perpendicular to SH mean. And what you will see is that that type of fracture is going to be that one. In this case, I have assumed that we have 3 points where the fracture starts, and eventually as they grow as independent planes, but eventually they are all in the same plane. This is just going to form one single fracture. And the third case is a wellbore which is drilled in the direction of SH mean. For this wellbore, if I take a cross section perpendicular to that wellbore and I analyze the stresses around the wellbore, depending on the conditions of stress anisotropy, SV minus SH max, I could have a condition in which the local least principal stress at the wall of the wellbore is the hoop stress, and that hoop stress, as you can see, is not going to be in the direction of SH mean. Actually, it's going to be perpendicular to that. So what is going to happen in that case? Because the local least principal stress, sigma theta theta, does not coincide with the far field least principal stress. Well, in this case, what is going to happen is that the fracture might start growing in the plane perpendicular to sigma theta theta, and eventually is going to turn in the far field to align with SH mean. And what you're going to see in ideal conditions is something like the following. In the far field, I have a plane which is perpendicular to SH mean, but as I get closer to the wellbore, the fracture changes direction. What actually starts here and changes direction as it goes into the far field. So let me repeat this over here. So this is going to be more or less like this, and more or less like that, where again, these two planes over here are perpendicular to SH mean, but the plane close to the wellbore is perpendicular to the least local principal stress, which in this case is the hoop stress. Well, this is not good for creating fractures because you are creating here a sort of a bottleneck where all your fluids have to go through, they have to rotate, and if you want propans to go through that, also that's not going to be very effective. This is going to create what is called fracture tortuosity, which is not desired for completions. So in order to get rid of these near wellbore effects, what you can do is you can do perforations in your wellbore. Notice that these perforations are going to be very similar to the wellbores 1 and 2. Let's call it perforation number 1 is going to be very similar to wellbore number 1. perforation number 2, horizontal, is going to be very similar to the wellbore number 2, because this is just like a little wellbore. And if I were to grow hydraulic fractures out of these perforations, this one will be already aligned with the far field stresses, that if they are far away from the wellbore, they are going to have their own stress change around the perforation that is going to favor the propagation, as we see in case number 2 like this, in case number 1 like that. And eventually, as they grow, they might grow into something like this that later converts into a hydraulic fracture that is in the same plane and it's perpendicular to the least principal stress, in this case, SH min. And if we take now this wellbore with perforations to this case over here, what I would see is that if I have several stages, those stages with fractures grown from these perforations, and that's what I would be preferable to have all these fractures which are independent, which are that start and grow perpendicular to SH min, so they are also independent, and that I can have as many fractures as possible in order to increase the surface area in contact of the wellbore. We're going to see that how close I put these fractures to each other, that's going to be something important, and it's going to be a design factor or parameter, which is called the fracture spacing or the stage spacing, something that we're going to see later on.